Okay, this is the overview I promised about the lab that we did in class on, was it Wednesday? And today we went over it in class. So uh, there were three possible chemical equations. We had sodium hydrogen carbonate, and sodium hydrogen carbonate might have made sodium hydroxide when it decomposed plus carbon dioxide, or it might have, sodium hydrogen carbonate might have made sodium oxide when it decomposed plus water plus carbon dioxide, or we might have had sodium hydrogen carbonate decomposing to make sodium carbonate plus water plus carbon dioxide. The idea of the lab is to try and figure out which one of these three equations is correct based on using a concept in chemistry called stoichiometry. It's spelled like this: stoichiometry. We have to balance the chemical equations. This one, of course, is balanced. Everything's even on both sides of the arrows. Over here, we need two of these sodium hydrogen carbonates because there are two NAs over here. So that gives us two C's. So we've got to put a 2 over here. Two there, and that's a balanced equation. Down here, there are two sodiums again. This time there already are two C's here and here, so we're even, everything's even except we just needed to put a 2 right there. Okay, using these numbers, these will be different from your numbers. I want you to use your numbers. So 14.13 grams is the amount of baking soda we had, including the weight of the crucible. So using my numbers here, if I subtract the weight of the empty crucible, I ended up with 3.13 grams. Okay, so that would be what you would put on this side for the mass of the baking soda, 3.13 grams. For the mass of the mass of the product, we would have had 12.97 grams, and we need to subtract from that the 11 grams. So you end up with 1.97 grams. Now we need to find moles of baking soda. So we would take our mass of baking soda, which is 3.13 grams of sodium hydrogen carbonate. We need to change it to moles. So we're going to put grams of sodium hydrogen carbonate on the bottom and put moles on the top. That's what we're looking for. We said that 1 always goes with mole, except in a mole ratio. 1 will always goes with moles. And we need to know the weight of the sodium hydrogen carbonate, that is the formula weight. So the sodium has a formula weight of 1. So you have 1 mole, and sodium has a weight of, sodium has a formula weight of 23. Hydrogen is 1. Carbon is 12, oxygen is 16, but there are 3 oxygens in the formula right here. You see 3 of them. So we'd have 23 plus 1 plus 12 plus 16 times 3, so our total is 84. So then we'd take our 3.13 and divide by 84. Doing that on a calculator here. 3.13 divided by 84. Whoops, 3.13 divided by 84 equals 0.037 moles. So our moles of baking soda, 0.037 moles. All right, so now we're ready to do the numbers using this lab, using the numbers that I gave you. Once again, you're going to use your numbers, the ones that you got in the lab, and I'm doing it based on the numbers that we have up here. So our predicted moles of NaOH, we know that we have 0.037 moles of sodium hydrogen carbonate, NaHCO3. To predict the moles, you need to go and look at the mole ratio in the balanced equation. So let's go back up to that. You'll need to flip your page over. This equation was balanced. Remember, there's a 1 here and a 1 here. So it's a 1-to-1 mole ratio. We know that if we have 1 mole of that, we're going to make 1 mole of that. So what we would do is use that ratio. You'd put moles on the bottom. So moles of NaHCO3 on the bottom, and you put moles of what you're looking for on top. Moles of...
Okay, I found something on the...
So we put moles of what we're looking for on top, which is moles of NaOH. Remember, it says to predict the moles of NaOH based on the moles of NaHCO3. And it was a 1-to-1 ratio, so the moles that were predicted were just 0.037 moles of NaOH. All right, now to find the grams of NaOH, we're going to take our moles of NaOH, 0.037 moles of NaOH. I'm going to put moles of NaOH on the bottom, put grams of NaOH on the top. Moles cancel, right here. So we do that, that cancels that. Then to find the actual mass of, actual mass of the NaOH that's in a mole, we'd have to take our weight of sodium. I had some trouble with my marker here. So sodium is 23, oxygen is 16, hydrogen is 1. 23 plus 16 plus 1 is 40. So now 0.037 times 40 is 1.48. So our predicted grams of NaOH is 1.48 grams. Okay, now that's an important number. We're going to go back and compare to our product. We got 1.97. That's not too far away, but I'm not sure it's close enough to say that that was the correct equation. So let's try a different one. Okay, in the second, and by the way, on your lab handout, D and E are in italics, F and G are not in italics, so they go together. And then H and I are in italics again to show that they go together. So now we're going to look at F and G. You're going to, again, predict the moles of sodium oxide like we did up here, but we predicted sodium hydroxide here. We want to predict sodium oxide in this step. So we're going to go back to our moles of baking soda, which was 0.037 moles of NaHCO3. We're going to put that on the bottom of the mole ratio. So moles of NaHCO3. On the top, you're going to put moles of what you're looking for, which was Na2O. Okay, now remember, I'm going to put a little line here to keep things separated. Maybe I am. There we go. Okay, so we're down here. So the moles of Na2O, if we go back up to our equation, you find Na2O's right here. See how there's a 1 right there? There's nothing there, but it's an implied 1, and then there's a 2 in front of the sodium hydrogen carbonate. So a 1 and a 2. That's what's called the mole ratio. It's a 1-to-2 ratio. So we'll come down over here, and we're going to put a, what I said was a 1 right there. So a 1 right here and a 2 right there. Now once again, how do I get the 1 and 2? Back up here. So 1 and a 2. So now we're going to end up with 0.037 times 1, then divide by 2. At 0.037 times 1, then divide by 2, 0.0185. So our predicted moles of Na2O are 0.0185 moles. Now we need to find the grams of Na2O, so we take our 0.0185 moles of Na2O, change that to grams. So what goes on the bottom? That'd be moles. What goes on the top? Okay, now we got to find our weight. So sodium is 23, so we're looking at 23 times 2. Oxygen is 16 times 1, so 23 times 2 and 16 times 1 is 62 grams for every 1 mole. So we take your 0.0185 and multiply it by 62, divide by 1, you get 1.15. So it turns out that 1.15 also, that's even further away from our 1.97 that we had in the lab. So then chances are that the second equation, this one, is not correct. So we know that this, our predicted amount of this did not agree with what we actually got. Our actual product mass was 1.97. And our predicted amount of NaOH was closer, but it still didn't really agree with it. So now we're going to try the sodium carbonate. So let's make the prediction. Okay, we know the moles of NaOH, or excuse me, NaHCO3 was 0.037. Not going back up here, 0.037. I'm going to start there again. So 0.037 moles of sodium hydrogen carbonate. On the bottom, we put moles of NaHCO3. On the top, you put moles of the sodium carbonate this time. Now, once again, this is called the mole ratio. So we're going to go, because it's moles over moles. And 1 always goes with moles, except in the mole ratio. Here it depends on the coefficients. So you go back up here, and you see what the coefficients are. So what's the coefficient in front of the sodium carbonate? 1. In front of the sodium hydrogen carbonate, it's 2. Okay. So we come down here. This is a 1, and this is a 2. So we're going to, 0.037 times 1 divided by 2 is 0.0185, just like it was a minute ago. This is sodium carbonate. But to find the grams of sodium carbonate, you're going to have a different formula weight, same number of moles. So 0.0185 moles of sodium carbonate. So you're going to put moles of sodium carbonate on the bottom. You're going to put grams of sodium carbonate on the top. And 1 goes in moles. If you add this up, it's 23 times 2, 12 times 1, 16 times 3. If you add those together, it's 46, 12, 48. You get 106. Raja? Okay, so now 0.0185 times 106. No. 0.0185 times 106. Is equal to 1.96. Well, that's pretty close, I think, to what we thought we were going to get. So let's put a circle around that before I get too crazy here. Hang on. All right. 1.96. Come back up here. Oh, look at that. The mass of the product was 1.97. So that means that the third equation was the correct equation. So here we go. So 1.97 was the actual mass of the product. We got 1.96. Once again, I know that because 1.97 was up at the top. Once again, you're going to do this with your numbers, not my numbers. So don't just be copying this. The predicted mass that was the closest was this equation C, EGI. So EGI, I was that one. All right, that means I from right here, see? And then the correct equation then must have been the third equation. So this is the correct equation, NaHCO3. We now know that it turned into...
In an organic, do you want me to keep...
we know this is sodium carbonate that we produced. So the white powder that was left in your crucible at the end of the lab with sodium carbonate. Now, and we have to balance it, of course, so I'll put a 2 there and a 2 over here in front of the CO2. So once again, 2 and 2. All right, so that's our balanced equation. So we use stoichiometry to try and decide which one of these three possible reactions for the decomposition of baking soda was correct. Turns out it was this equation, we got almost perfect results with these numbers, and your numbers should be very close as well. All right, so again, use your numbers, my numbers. If you need to rewind this and watch, please do. You should have this done when you come to class next. Thanks.